Newton's universal law of gravitation basically told us that if you take any two objects, no matter where they are in the universe, as long as they both have mass, they will pull on each other through the force of gravity. And this law has served us very well. It turns out to hold very true. We make great predictions with it that turn out to be very accurate. But scientists at the time didn't love this idea. There was something that just seemed a little creepy, a little bit off about it to them. This idea that two objects can pull on each other even though they could be in totally different places and not in contact. Most of the forces we experience on a day-to-day basis work through contact. Friction works when one object exerts a friction force on another by being in contact and sliding or rubbing. The normal force works when the floor is in contact with your feet, for example. Tension in a rope works if the tension is attached to you, the rope, is attached to you and pulling on you. You can't pull someone with a rope unless the rope's attached to them. So almost all the forces that we experience daily and that we're used to and that we have a good intuition for work by being in contact with you. So this idea that gravity could work without two things being in contact didn't sit well with a lot of scientists. So people came up with sort of another way to explain this. And the idea they came up with was gravitational fields. And the idea basically goes like this. Let's say we have two objects. Maybe in front of you, you've got a screen and your hand. Why don't you for now place them so that your screen and your hand are not touching each other? They have some distance between them. Now, what scientists sort of said might be happening here is that rather than the screen and your hand magically pulling on each other, even though they're not in contact, maybe the screen creates this thing around it called a gravitational field. This isn't something we can see. It's not something that has any mass. It's not something we can touch. It's basically invisible. It's practically just an idea in our heads, but it's all around the screen, and it's created by the screen. And now when your hand comes along and goes in that gravitational field, it feels a force towards the screen. But scientists said it's not being pulled by the screen directly, it's being pulled by the gravitational field that the screen creates. So the screen is in contact with the gravitational field, which it created. Your hand is in contact with that gravitational field and then gets a pull from the field. So these things all, if we think of it this way in terms of fields, everything is sort of in contact, even if it's indirect. So this idea of fields kind of put a few people at ease, and they said, you know what, I can get on board with this whole gravity thing as long as we think of it as fields and not just objects randomly pulling on each other magically. It turns out that the idea of fields is useful for a lot more than just making a few scientists happy back in the day. So it's an idea that's persisted and that we've continued to develop. So if we're going to properly define this, I would say a field is an area of influence. Right? It's an area, a region around your screen, for example, where it can influence other things, like your hand by pulling on it. If we get rid of the hand and screen example for now, let's look at something else. Let's look at a campfire. And it seems as though a campfire emits something that we could call a heat field. In the area around the fire can influence things by making them hot. It creates an area of influence, a field. So what you would notice, if you sort of like started over here and you walk towards the fire, as you approach the fire, you would notice that the strength of the fire's heat field increased. Field's strength increases. And the way you can detect that is because your temperature goes up. So now let's say instead of walking towards the fire, you kind of stay in one place and someone pours a bunch of gas on the fire. So the fire, it gets enlarged. And you'd again probably notice the same thing happens. When someone pours a bunch of gas on the fire, if you're sitting in the same place, you're going to feel that your temperature increases. The strength of the heat field created by this fire increases. So this is a way of thinking about a fire, that there's sort of this region around the fire that's always there, that's always ready to make things hot. But it's not, if there's nothing there to be hot, there isn't actually a temperature at that point. It's not until something steps into that field, into that region around the fire, that we have a temperature and we can measure it. Just as a fire creates a heat field, every mass creates a gravitational field. And so there's some similarities, but some differences between these fields. Heat fields cause objects to have a temperature, whereas gravitational fields cause objects to feel a force. So if I place an object in my fire's heat field, it gets a temperature. If I place an object in Earth's gravitational field, it feels a force. Now, one difference between these fields is in the sort of quantities they have, or that they are. A heat field is a scalar because temperature is a scalar. So if we look at our heat field above in the fire, I could actually kind of map it out if I wanted to. So maybe right beside the fire, if I put an object there, it would get a temperature of 70 degrees, right close to the fire. And if I put an object over here to the right a little bit further away, maybe it would get a temperature of 60 degrees. And then if I put an object even further away, maybe up here in the corner, say it would get a temperature of 50 degrees. So these numbers represent the strength of the heat field. And we can see that close to the fire, the heat field is very strong. Further away from the fire, the heat field is more weak. We'd like to be able to come up with a similar map for gravitational fields. But the problem is, a gravitational field is a vector, because gravitational fields create force, and force is a vector. So just putting numbers around this page over Earth over here, like I did for my fire, isn't going to work, because numbers, like the ones I did up here, can't convey direction, and direction is important. So there's another way we draw gravitational fields that looks a bit different. And it is like this. Okay, so these arrows I've drawn around the Earth, they clearly show direction. We can tell from these arrows the direction of the gravitational field. If I'm over here, the gravitational field is going to the right. If I'm over here, the gravitational field is going down and to the left. But magnitude's important as well for vectors. And so how can I tell the magnitude of this field by this diagram I've drawn? Well, we can't get a precise reading of it, but we get a sense of where the magnitude is large and where the magnitude is small. And we do that by looking at the density of the arrows. The density of these arrows represents the strength of the field. So, for example, right here on the surface of the Earth, those two arrows are pretty close together. And these two over here are pretty close together. The arrows are dense, so the gravitational field is strong. But out here, higher up, these arrows are quite further apart. And these arrows over here are quite far apart as well. So the arrows are less dense up there high above the Earth. So the gravitational field is less strong. And in that way, with these arrows I've drawn, I get a sense of both the direction and the magnitude or the strength of this gravitational field at the same time with one picture. Now, just a quick reminder, gravitational field strength has another name. It's also called acceleration due to gravity. This is due to something that's a little bit weird about how our universe behaves or how our universe was created. What it basically means is if I take a point, say right over here on the surface of the Earth, if I find the strength of Earth's gravitational field right at that point, I'll get 9.8 newtons per kilogram, meaning if I put a 1 kilogram object there, it'll feel a force from the field of 9.8 newtons. Now, interestingly, if I then take that object and I let it go and I have it fall towards Earth, it'll accelerate at 9.8 meters per second squared. That's not a fluke that those two numbers are the same. It's like that everywhere in our universe. The strength of a gravitational field is a number, and that number is the same as how quickly an object will accelerate if you place it there. On the surface of the moon, the strength of the gravitational field is 1.6 newtons for every kilogram. And if you take an object and you place it near the surface of the moon, you hold it up and you let it go, it'll fall to the moon accelerating at 1.6 meters per second squared. So these two things are actually the same. The strength of a gravitational field and the acceleration due to gravity. Two names for the same thing. And we use the same symbol for both of them, and that symbol is little g. So with that in mind, let's think about some formulas we have for little g. Now there's sort of two relationships that mass has with gravitational fields. If you remember when I had you thinking about your screen and your hand in front of you, there were two different objects there that I needed to sort of convey this idea. Your screen was the one that we said is creating a gravitational field all around it. And your hand was the object that was sitting in that gravitational field and being affected by it, being pulled by the gravitational field. So mass can create fields. Mass is also affected by fields it's sitting in. Now this works both ways. Just like your screen is producing a field that affects your hand is also producing a field that affects your screen. But sometimes we just focus on one side or the other. Anyways, this way that mass has these two relationships with gravitational field is sort of represented in two different formulas that you will have seen before. Here's one. And here's the other. So two formulas that have little g in them. Little g is gravitational field strength. It's also called acceleration due to gravity. And you notice that mass appears twice in these. There's a mass and there's a mass. But these are different masses and they're doing different things. This first mass is the mass of the object creating the field. And this other mass is the object affected by the field. So if I wanted to know, for example, how hard your screen was pulling on your hand, I would take the mass of your screen, the object creating the field, and put it there. I would then use that to find how strong the gravitational field is that it's creating. And then once I knew that, I'd take that number and I'd put it over here, and I'd say I have your hand, this object, sitting in that gravitational field that's already been created, and I'd find out the force on your hand. So my first equation over here tells me the strength of a gravitational field created by an object. And my second formula tells me the force that another object will feel if it's in that gravitational field. So two different masses, the one creating the field and the one affected by the field. We can also combine these two formulas in this way over here, that I'm going to show you in a moment, to get something different. We take the second formula, and for that little g, we say, well, maybe I don't know what that is, but I can find it using this first formula. So we sub that first formula in to the second formula. Instead of little g, I write the formula I can use to calculate it. And that gives me But remember, these two masses I have here are different. One was the one creating the field, one was the one affected by the field. So I should give them slightly different names. And I'll call them M1 and M2. And now this formula should look very familiar. This, Fg equals M1, M2, big G over R squared, is Newton's universal law of gravitation. So what I've kind of showed here is these two ways of thinking about gravity are actually giving us the exact same results. I can think about gravity the new way in terms of fields, where I have an object that creates a gravitational field, and then a second object that sits in that field and feels a force from it. Or I can think of it the way Newton did and just said, I've got two objects, and magically they're some distance away from each other, and they're pulling on each other with a force. And it doesn't matter which of these two ways I think about it, the Newton way or the Fields way, I get the exact same result. We got Newton's equation by simply combining the two Fields equations. So these are just not two different really theories on gravity or two different ways to deal with gravity. They're just two different ways to think about it. And I'll just write a note here about these two M's being different. All right, so let's look at an example here. What is the gravitational field strength on the surface of the moon? So we haven't said there's any objects there. We've just said, here's a location near the moon. What's the strength of the gravitational field there? So this is a situation where we have an object, the moon, creating a gravitational field. We don't yet have an object sitting in the gravitational field feeling it. We've got just an object the moon that is creating it. So let's use our formula for the gravitational field created by an object. So, again, this mass is the mass of the object creating the field. So in this case, that's the moon. Big G, as usual. And R is the distance from the center of the object to wherever we're measuring the field. So because we want to know the field on the surface of the moon, we want the distance from the center of the moon to the surface, and that is just the radius, which is what's given to us. And plugging this into our calculator, we get 1.62. And now we got to sort units. Well, remember I said little g had two different formulas and two different names. If I use this formula over here and I rearrange it for little g, I get newtons divided by kilograms, or newtons per kilogram. So if I'm thinking of little g as the strength of a gravitational field, that's usually the units I will use. Newtons per kilogram. It's the number of newtons of force a 1 kilogram mass would feel from the field. So if I have a 1 kilogram mass near the surface of the moon, it'll feel a force of 1.62 newtons. Now the other units I can use are meters per second squared. Because remember, the other name for little g is acceleration due to gravity. And like I said before, if you went to the surface of the moon and you took an object, doesn't matter how much the object weighed, you lift it up above your head and let it go, it would accelerate at 1.62 meters per second squared. So this quantity, little g, has two names: acceleration due to gravity and gravitational field strength. It also has two versions of its units: newtons per kilogram and meters per second squared. Because these two units are actually completely equivalent, they're just different ways of saying the same thing, you can really use whichever one you want. However, there is a bit of a convention. We tend to use this first one when we're talking about little g as gravitational field strength. And we tend to use this second unit, meters per second squared, when we're talking about little g as acceleration due to gravity. All right. So now that we kind of have a sense of how gravitational fields are strong when we're close to an object, and they're a bit weaker when we're further away from an object, and we know from a previous lesson a little bit about how orbit works, let's talk about one more application of orbit and kind of kick things up a notch a bit. I want to talk about geosynchronous orbit. But first of all, let's do a little intro here. So the orbital speed of a satellite is a finicky thing. If the satellite goes too slow, it doesn't have enough speed for its arcing fall to match the curvature of the Earth, and it'll crash into the planet. Similarly, if it goes too fast, it'll zoom away from the planet and float off into space. So at a certain height, at a certain orbital radius, there's only one speed you can go while staying in orbit. You can't go too slow, you can't go too fast. And we can actually come up with a formula for the speed you have to go to stay in orbit pretty quickly. So remember, orbit is an example of circular motion. So we can start with F equals ma. But it's a type of circular motion where the only force the object feels is the force of gravity. That'll be the centripetal force. It's pulling them towards the center of the object they're orbiting. Because it's a circular motion, we have a centripetal acceleration, AC. Now we can elaborate a little bit because we know that force of gravity can be calculated as m1, m2, big G over r squared. And we have a couple formulas we can use for centripetal acceleration. We're trying to come up with a formula for speed. So let's pick a formula that has speed in it. V squared over r. Again, there's two masses here. They're slightly different. It doesn't really matter which one we call which, but I like to use the convention that m2 is the bigger mass, or m2 is the mass creating the gravitational field. So in this case, that's going to be the Earth, and m1 is going to be the thing that's orbiting the Earth. We'll call it a satellite, although the question didn't specifically say. So this is Earth. And this is my satellite. Now we've got another m. This m over here. Which one is that? Well, that's the m from F equals ma. So that's the m that was feeling a net force, and it's the m that was accelerating. It was the m that had the centripetal acceleration. So that's my thing that's moving in a circle. So that's going to be not the Earth. That's going to be the satellite. So this m is the satellite. Now, the reason it's important to identify which m's are which is because some of them are going to cancel out. Notice on the left side and the right side, I have the mass of the satellite and the mass of the satellite. So I cancel those both out. Then I remind myself I'm trying to come up with a formula for speed. So I want v to be isolated all by itself. So I'm going to take this r and move it over to the other side, although I'm realizing now that I can actually do some canceling with the r's too. If I multiply both sides by r, that goes away and that goes away. I've effectively got two r's here in the denominator, r times r, because the r is squared. So when I multiply both sides by r, I get rid of one of them. I no longer have r squared, I just have plain r. So now let's take that formula and let's rearrange it for v. Get v on one side all by itself. Well, I should get m2 times big G divided by r square root equals v. So what this means is if you have an object in orbit and you want to know the speed it has to go at to be in orbit, all you need to know is the mass of the thing it's orbiting and how far it is from the center. It doesn't matter how heavy the thing is that's orbiting. It doesn't matter if your satellite is the size of a grain of sand, or if it's the International Space Station, or if your satellite is the moon and you want to put it into orbit. All these things will orbit at the same speed as long as they're orbiting at the same distance from Earth. So I want to talk about another thing this means. If changing your distance from the object you're orbiting means you have to go a different speed, that leads us to something interesting. So let's say we've got the sun over here. And we've got a few things orbiting around the sun. Let's say we've got Mercury. One of our first planet orbiting around the sun. And let's say a little bit further out, we've got Earth. And a little bit further out, we've got Neptune, way out here. All of these are going in circles around the sun. I haven't drawn the actual circles out. So there's Mercury, there's Earth, there's Neptune. All of these are orbiting the same body, the sun. So they all would have the same M2. But all their orbits have different radii. Mercury, this first one, is orbiting at a really small radius. Earth is orbiting at a bigger radius. And Neptune is orbiting at the largest radius. So what you'll notice in this formula up here is because r is in the denominator, as r gets bigger, this whole side gets smaller, which means v is getting smaller. So the larger your orbit, the further you are away from the object you're orbiting, the lower your speed. So Mercury is going to have a pretty fast speed. Earth is going to be going a little bit slower, and Neptune is going to be just chugging along, hardly moving at all. This can sometimes seem sort of counterintuitive. People think, well, look at Neptune, it's way out here. Look how far it has to go to do a whole loop around the sun. It's going to have to really go fast to cover that whole thing. No, Neptune is barely moving at all compared to Mercury, which has this tiny distance to go around, but it's going to do it very, very fast and make many, many loops in a short amount of time. Okay, so that's the first thing I want you to realize, that the lower your orbit, the smaller your orbit, the faster you have to go to be in orbit. So if satellites at different heights have different orbital speeds, we should be able to choose a height so that the satellite has the same period as Earth's rotation. So remember this, I drew an example up here of the sun, but we could just as well imagine, rather than these being planets orbiting the sun, we could imagine that they're satellites orbiting the Earth. And the Earth is rotating. So imagine this thing rotating, say, clockwise, slowly, and it goes once around every 24 hours. Well, as this object rotates around, this is the fast satellite with the high speed. It's just whipping around there. It maybe does like 10 loops in the time it takes this object to go around once. But over here, this object is barely moving. It's going so slowly. So this guy could probably rotate several times in the time it takes that satellite far away to go around once. So for the inner satellite, it's going to do way more loops than the object does. The outer satellite is going to do way less loops than the object does. But in between, somewhere, there's going to be a happy medium where we could put a satellite and it would go once around in the exact same time it takes my rotating body to go around once. And if we do that around the Earth, it's called geosynchronous orbit. The time it takes my satellite to go around once is the same as the time it takes Earth to rotate once. Now, what's weird about this is if you were standing on Earth underneath one of these geosynchronous satellites, and you looked up at the satellite, it would appear to you to not be moving. Because although the satellite is doing a loop around the Earth is rotating at the same rate. So you would always be able to look straight up and see that satellite. It would appear as if it's just kind of frozen in the air above you. And you'd be expecting it to fall because it doesn't appear to be moving, so it doesn't appear to be orbiting, but it never does. So this is called geostationary or geosynchronous orbit. And I was saying it happens at a very specific height. Let's find that height. So a satellite is geostationary above Earth's equator. Find the orbital radius of the satellite. So back to our usual approach. F equals ma. My force on this satellite is going to be gravity. It's going to come from m1, m2, big G, divided by r squared. And the acceleration of this satellite is going to be 4 pi squared r over t squared. The reason I've decided to use this formula is because I don't know yet what the radius of this orbit is going to have to be. And I don't know what the speed of this orbit is going to have to be. The one thing I know is it has to go around once in the same time as it takes the Earth to go around once. So I know its period. That's why I picked this formula, because it has period in it, so I get to use that piece of information that I know. So again, mass of the satellite on both sides cancels out. I'm trying to find the radius, so let's take both of these r's and put them on the same side. I'm going to take this r down here and move it over to the other side, and then I'll move everything else to the left. So that gives me m2 big G divided by 4 pi squared. And I've got a t squared that comes up to the top. And this is all equal to r cubed. When I take this r squared down here and I move it up beside this r, I get r squared times r, which is r cubed. So let's plug some numbers in here. I wanted to, m2 is the mass of the Earth. So 5.97 times 10 to the 24. Big G is 6.67 times 10 to the negative 11. Now the period of this satellite, the time it takes to go around once, well, I want that to match Earth. So, well, it takes Earth 24 hours to rotate around once. But I want that in seconds, so I'll multiply it by 60 to get minutes, and then by 60 again to get seconds. And then I divide this by 4 pi squared. And then I have to, if I want to get regular r and not r cubed, I have to take the cubed root of this whole thing. And that gives me 4.22 times 10 to the 7 meters. So if you want to be in geostationary orbit, if you want to appear to always be above the same point on the Earth, on the equator, you have to make sure your satellite is this far from the surface of the Earth, which is actually pretty high up. Most satellites, I think, orbit much lower than that. You don't have to go nearly that high to get an orbit. That's just how high you have to go to get into geostationary orbit. So it's one thing to get the satellite up that high, but then you got to get it moving, because if you just bring it that high and let go of it, it falls back to Earth. So how fast are we going to have to get this going? to then keep it in orbit? Well, there's a few ways we could tackle this, but because I know the radius of its orbit, and because I know its period, I actually think the easiest way to solve this equation, or to solve this problem, is this. Just saying that speed is distance over time. The distance this travels as it goes once around its orbit is the circumference, or 2 pi r. And the time it takes to go once around is the period, or t. So this is 2 pi, and there's my r. And then the period, again, is 24 times 60 times 60. Pardon me, I'm jumping the gun here. Right, that's better. So the answer, if I round it to three sig figs, is 3,000. Well, let's go one more. 3,069 meters per second. So, if I want to put something in geostationary orbit above Earth's equator, I need to first go to this height above Earth's center, and then I need to get my thing going with this much speed. It doesn't matter how big that object is. If it's at that height and going that speed, I can put it in geostationary or geosynchronous orbit. Now, one thing I'm just realizing I forgot to write down, even though I did it in my calculation, was over here in this previous part of the question. The period is supposed to be squared. I wrote that here, but I didn't write it here. I did it in my calculation, but I did not do it when I was writing it down. So let's just add that right now, that little squared in there. One other thing I'll say is if you actually look up the period of Earth's rotation, you get a number that's just slightly different than 24 times 60 times 60. I don't want to go into too much detail about why that is, but it has to do with the fact that as Earth rotates once around, it also moves because it's going around the sun. So even if you do one full rotation, because you've moved to a slightly different spot in your orbit, the sun is not in the same place in the sky as it was when you started that rotation. So you actually have to rotate a little bit further than once around to get the sun back at the same point from your perspective. So that's why, for Earth to rotate around once is actually just a little bit less than 24 hours. 24 hours is how long it takes to rotate once around, and then plus a little bit more to get the sun back in the same spot. But the difference between the official number and the number we calculate this way for Earth's period is pretty small. It's a difference of 1 or 2 digits in that third sig fig. So it's not going to make a significant difference for us. And before we go, I'll just pull up this picture here of our solar system. This is very much not to scale, but it gives you an idea of the key planets and where they are. And I want to point out one interesting fact. So we said that objects that were close, that had small orbits, that were close to the object they were orbiting, had the highest speeds. So here's Mercury, which is just hoofing it. It's got a speed in that direction. And then if we look at, Saturn, it's got, some speed, but a little bit less. And if we look at Neptune, it's even less. And Pluto, which used to be a planet way out here, is just, the furthest one away. It's got the tiniest amount of speed you can imagine. And a fact I actually heard about Pluto is between the day when Pluto was first discovered, the first person saw it, and identified it as a planet. Between that day and the time when Pluto was deemed later on, decades later, to no longer be a planet. For the whole time Pluto was recognized as a planet, decades and decades, it didn't even make it all the way around the sun once. I think it wasn't even close. It just made it a fraction of the way around the sun the entire time we were considering it a planet. Meanwhile, Mercury had probably gone around the sun maybe 100 times in that time frame. So I'm just trying to drive home this idea that if you want to orbit close to something, you have to go fast. And if you want to orbit further away, you have to go much, much slower. And that's all for this lesson.